Today we are going to discuss the paper Lora Low-Rank Adaptation of Large Language Models. This paper introduces a new method to efficiently fine-tune large language models without updating all their parameters. Instead, it injects small trainable low-rank matrices into each layer of the model, significantly reducing the computational cost while maintaining performance. Fine-tuning large models like GPT-3175B is expensive. Every time a model is fine-tuned for a new task, all its parameters are updated, requiring vast amounts of memory and computational power. Deploying multiple versions of a fine-tuned model becomes impractical due to storage and switching costs. Traditional methods to mitigate this, such as adapters or prefix tuning, either introduce additional latency or reduce the effective sequence length, making them less ideal for real-world applications. Lora solves this by keeping the pre-trained model frozen and training only small rank decomposition matrices. Instead of updating the entire weight matrix, it expresses the update as the product of two smaller matrices. This drastically reduces the number of trainable parameters by up to 10,000 times in the case of GPT-3175B and requires 3 times less GPU memory. Unlike adapters, Lora does not introduce additional inference latency because its changes can be merged back into the original model weights. The core idea of Lora comes from the observation that pre-trained language models operate in a low-dimensional space. Instead of modifying the full-rank weight matrix, Lora learns a low-rank update, capturing only the essential information needed for adaptation. It is applied primarily to the attention layers in transformer models, particularly to the query and value projection matrices, which significantly impacts model performance. Lora has several key benefits. First, it allows multiple task-specific adaptations while keeping the core model unchanged, reducing storage requirements and making task switching much more efficient. Second, it lowers the hardware barrier to fine-tuning since only a small subset of the parameters needs optimization. Third, unlike methods such as adapters, Lora does not slow down inference because the updated matrices can be merged with the frozen pre-trained weights. Despite these advantages, Lora has some limitations. It does not yet batch inputs from different tasks with different Lora modules in a single forward pass when the weights are merged. Also, while it performs well on many tasks, it may not be optimal for scenarios where the pre-trained model requires extensive adaptation beyond low-rank transformations. Empirical results show that Lora matches or even outperforms full fine-tuning across multiple models, including Roberta, DeBerta, GPT-2, and GPT-3. On GPT-3, 175 billion, Lora achieves the same or better accuracy as full fine-tuning, while using only a tiny fraction of the trainable parameters. The experiments also confirm that the weight updates in fine-tuning are inherently low-rank, supporting the fundamental idea behind Lora. To summarize, Lora provides a scalable and efficient method for fine-tuning large language models by leveraging low-rank updates. It significantly reduces computational cost while maintaining model quality, making fine-tuning accessible and practical for real-world applications. It is an elegant solution to a pressing problem in the field of deep learning, allowing us to adapt large models efficiently without the usual resource constraints.